Chapter 16, Lesson 5. And in this chapter we've been talking about acids and bases, and especially acids and bases through the eyes of equilibrium. So we've given both the Ka, the equilibrium constant for the dissociation of an acid, and the Kb, the same thing for the base. And we said in general, weak acids are given Kas and Kbs, and weak bases are given Kbs, because weak acids and bases do not dissociate completely. So HF, for example, here is seen to have a Ka of 6.8 times 10 to the negative fourth. This means that most of the substance exists on the reactant side. Very little product at equilibrium exists, which means very little of the H plus actually dissociates, but enough so we can talk about it. Now, we began the discussion around conjugate acids and bases, and we said every acid, in this case HF again, has a conjugate base, in this case F minus, and the conjugate base is what results when the acid gives up its proton, and that conjugate base has a basicity, has a corresponding basicity. It turns out that the Ka and Kb of the conjugate acid and base pair are actually related, and the relationship is through the Kw, or the acid-base, the dissociation constant for water. This is pretty powerful because if you know the Ka of an acid, you automatically know the Kb of its conjugate base. And this again reiterates the idea that this acid and base concept is based off of water. Water is really what the acid and base concept circles around, if you would. So in fact we can do this. Here we're asked to find the acid dissociation constant for hypochlorous acid Ka. Now it turns out, if you take a look in the back of your book, this would be in Appendix D, hypochlorous acid is given a Ka in the back of the book. The Ka of hypochlorous acid is given as 3.0 times 10 to the negative 8. And if you take a look, this is from Appendix D. In the back of the book. However, we can make the same exact calculation if we had the Kb of ClO minus. And earlier in the notes, in fact I'm going to cycle back real quick, I'll show you where it's at. If you take a look, here we give the hypochlorite ion, this substance here, acting as a base, because it accepts a proton from water, becoming this hypochlorous acid, HClO. Its Kb is given as 3.3 times 10 to the negative 7. So let me show you how this can give us the Ka of HClO, 3.3 times 10 to the negative 7. So the Kb is 3.3 times 10 to the negative 7, and we said that Ka times Kb gives you Kw, which means Kw is simply Kb over Ka. I'm sorry, let's try that again. Ka, which is what we want to solve for, is Kw over Kb. The writing is a bit messy, but so our Ka can now be derived from the given Kb earlier in the notes. And in this case we have Kw, which is a constant, the dissociation constant of water, 1.0 times 10 to the negative 14, divided by 3.3 times 10 to the negative 7. So go ahead and plug this into your calculator and see whether you can verify the Ka of our acid. So 1.0 times 10 to the negative 14 divided by 3.3 times 10 to the negative 7. And we should get ourselves 3.0 times 10 to the negative 8. That is verified. So we proved here that Ka and Kb The Ka and Kb constants are related, which is pretty powerful idea. In fact, you can use this to solve many different acid-base problems, as we'll see. Now, because we've defined anions as bases, in other words, conjugate bases, so again, HF being an acid leads to a conjugate base, which is F minus. We can now think of these anions as bases in their own right. So if you take a look, F minus can actually be a real base. Its Kb is pretty small, and that's because the Ka of HF is big by comparison. And so if the anion comes from a weak acid, it itself will have some basic properties. Now here Cl comes from a strong acid. Cl minus came from HCl, there he is, and so this means the anion Cl minus, being from a very strong acid, has negligible basic properties. Its Kb is so tiny we don't care, just like the Ka of HCl was so huge that we didn't really care. So the lesson here is the stronger the acid, the weaker its conjugate base. And as a rule, weak acids or bases will have formidable conjugates. In other words, their conjugates are going to be acting as acids or bases. So here we're going to go through some additional theoretical considerations of acids and bases. First of all, anytime you have yourself a cation in water, so think of a positively charged. Remember, cations are positively charged. The cation will be hydrated. The cation will pull toward itself water molecules because of the positive charge. The negative side of the water molecule, which comes from the oxygen, will actually pull toward itself the positive charge, and as these attract, the electron density from the hydrogen then on the water gets pulled together as well, and the hydrogens can then pop off. And if the hydrogen pops off, you have yourself acidity. Therefore, the pH of the solution gets lowered. And notice here you have a +3 charge. This is a very big effect. A +3 ion, like aluminum +3, has a very big effect on the pH of a solution because of this pulling away the electron density from the hydrogen of water. So this is a little bit of more of a explanation of the same phenomenon. So go ahead and fill some stuff in here. So again, the greater the charge, +3 in this case, and the smaller the size, make a cation more acidic. And this is kind of back to our idea of lattice energy. Remember, we said if you want a strong attraction between charges, you want a high charge, great charge, and a small size. That way those charges can fit together closely, more closely. And so this is kind of an explanation of the idea. In fact, if you take a look at these 4 solutions, here are nitrates of 4 different metals: sodium, calcium, zinc, and aluminum. And you'll notice right away that the pH of the sodium solution is pretty neutral, actually exactly on the spot. The pH of the calcium solution is slightly lower, tiny bit. Calcium, recall, is a 2+ charge. Zinc here has quite a bit of a drop in pH, and zinc also is +2. But because zinc is further along on the periodic table, more toward the right, recall that as you go across a period, the size decreases. So zinc is actually smaller than calcium and pulls more electron density away from the hydrogen of the water molecules. And then aluminum, notice here, is +3. Also being small, aluminum is actually a group up the periodic table, or not a group, I'm sorry, a period up, so it's in the lower energy level, meaning it's smaller still and a higher charge. So aluminum decreases the pH down to 3.5, and this is the range for weak acids. Weak acids generally produce this sort of pH, and so aluminum just as a metal, is able to do the same thing. And you've got, for your visual pleasure, a few colors here, and this is using a universal indicator. Usually your red are your acids and your blue are your bases. So here's kind of a summary of the idea. An anion that is the conjugate base of a strong acid will not affect the pH. So that would be HCl is a strong acid, and its anion Cl- won't have any effect on the pH. An anion that's the conjugate base of a weak acid will increase the pH, meaning if you have yourself an anion like HF, which is a weak acid, producing an anion of F-, well, because this is a weak acid, it'll produce a weak base as its conjugate, therefore increasing the pH, because recall, bases have high pHs. A cation, that's the conjugate acid of a weak base, will decrease the pH, and this is kind of what we just seen. So your aluminum plus 3, you can say, will decrease the pH of a solution. Cations of the strong Arrhenius bases will not affect the pH. What this means is, if you have sodium hydroxide, the cation of this strong base is sodium, and sodium will not affect the pH in general. And most of these Arrhenius bases come from group 1, so you have potassium hydroxide, rubidium hydroxide. Even things like calcium hydroxide don't really affect the pH by that much, by a little bit, but really not by much. These are your group 1, group 2 metal ions. Other metal ions will cause a decrease in pH. We just seen that, like aluminum especially. And then finally, when a solution contains both the conjugate base of a weak acid and the conjugate acid of a weak base, if you mix the two, then the pH will depend on how strong the original acid was and how strong the original base was. So you'd have to take a look at their Ka and Kb values, because recall, these values tell you roughly the strength or weakness of a acid or base. And this is kind of a summary of looking now at the whole idea of acids and bases from both directions. Really a much more mature understanding of acidity. So why don't we try a little example to solidify this understanding. Here it says predict whether the solutions of each of the following salts are acidic, basic, or neutral. So if you take a look at potassium, the way to think about this is think of the two parts of the salt, in this case potassium plus and carbonate 2-, and think where they might have come from. Well, if you think that potassium plus is the conjugate of, or is the leftover of potassium hydroxide, we know that potassium hydroxide is a strong base. And what's left over then will be non-acidic, because the base was so strong, all of it dissociates and none of it goes back together. By contrast, CO3 2- came from carbonic acid, you could say. It originally came from carbonic acid. It turns out it actually came from hydrogen carbonate, which has acidic properties, but it is a weak acid. It being a weak acid then produces a weak base, and carbonate will be weakly basic. And if you recall in class, we showed how carbonate, sodium carbonate or potassium carbonate, creates a basic solution. So this guy will definitely be basic. NABR, if you take a look, if we analyze NABR for the same idea, sodium comes from a strong base, sodium hydroxide, so it does nothing. Now bromine actually comes from HBr, which is also a strong acid, and being a strong acid, it produces an anion, a conjugate base that's negligibly basic. So no change there. This should provide for us a neutral pH. Right, let's keep going. NH4Cl gives us, the Cl comes from HCl, so Cl will not affect the solution by much because HCl is a strong acid. NH4, however, NH4 plus, in this case ammonium, is the product of a weak base. NH3 being a weak base produces NH4 plus. So NH3 being a weak base, then from the other side will cause acidic properties. Its conjugate will have acidic properties. So this should be acidic. I know we're kind of running out of room here, but we've got a few more to consider. Aluminum nitrate. Nitrate coming from nitric acid will not cause any basicity because nitric acid is strong. Aluminum, however, being a +3, creates a strong positive charge in solution. The water molecules are attracted, their hydrogens pop off, and this creates an acidic solution. And finally, potassium phosphate. You can again think of phosphate. Let's think about this up here. You can think of phosphate initially coming from phosphoric acid. Phosphoric acid we know is a weak acid, and phosphate actually comes from, after a few of these hydrogens come off, you get H2PO4 minus 1, then HPO4 minus 2, and only then do you get to phosphate. Only then do you finally become PO4 minus 3. So if H3PO4 is a weak acid, H2PO4 is even more weak, HPO4 is even more weak, therefore this guy will be a pretty considerable base. It won't be a strong base, but it will be very considerably basic. In fact, you can look up his Kb and you'll see it's pretty formidable. So this will create a basic solution. So this is a good way of looking from both directions at this idea of acids and bases. We're going to wrap up with a few more considerations. So in general, the periodic table can be a good guide in showing acidic and basic properties. In fact, we mentioned this earlier, and we said in general, as you go from left to right, what you're doing is you're increasing from metals to non-metals. You're becoming more non-metal-like, and non-metals are considered to be more acidic. So that's why as acid strength increases as you go from left to right, because you go from metal to non-metal. If you recall, metals are, you can think of them more having basic character. Non-metals, you can think of them having more acidic character. And then same thing if you go down, except here it kind of deviates from our idea. So here it says we're increasing in acid strength as we go down the periodic table. Now as we go down the periodic table, in general, the non-metals are at the top, the metals are at the bottom, so this is actually reversed. And the way to think about it here is the idea of polarity. As you go down, the polarity between the hydrogen and the chlorine increases, the difference in electronegativity increases, which means the hydrogen can more easily be pulled off. Actually, in this case, let me reiterate that it's not the polarity. As we go down the periodic table, it's the size that gets bigger and bigger and bigger. So here, the size actually has a big effect, because if you think of a big atom bonded to hydrogen, the hydrogen is, you can say, further away from the nucleus and can more easily pop off. And so your HCl is stronger than HF. And there are a few of these concepts kind of built in. Here it says the weaker the HX bond, the more acidic the compound, meaning if it's a weak bond, that means the hydrogen can pop off more easily. So these are the basic trends on the periodic table. For oxyacids, recall, are acids based on the polyatomic ions. The general trend is also, in a way, considered. You can think of this as electronegativity also having playing a role, but in general, what you'll see if you take a look at the three oxyacids, ClO, BrO, and IO, you'll see that the Ka of the acids decreases. In other words, you're getting weaker and weaker and weaker going this way. So the more electronegative element, chlorine is more electronegative, is able to pull the electron density more away from the hydrogen, you can say, through the oxygen. So with oxyacids, the trend is reverse. And finally, if you think of just a series of oxyacids, like think of a chlorate, ClO, between chlorine and oxygen, the more oxygens you add, from 2 to 3 to 4, the stronger the acid. So notice your perchloric acid, and we consider perchloric acid to be strong, chloric acid is to be strong as well. So as you increase the strength of the acid, as you add more oxygens, the acidic strength increases. So your hypochlorous acid is a weak acid. Notice it's tiny, tiny Ka value. The more oxygens, the more acidic in general. And finally, we're going to introduce, we're not going to do much with this, but we're going to introduce a class of compounds called Lewis acids and Lewis bases. And these are actually very important, and they're very important in that they are able to describe a set of reactions that aren't well described by the regular acid-base definitions. So the Lewis acid, and Lewis was G.N. Lewis, a famous American chemist, G.N. He did it in terms of electron pairs. So a Lewis acid is defined as an electron pair acceptor. So here, if you take a look at the Lewis acid, a Lewis acid will have a lone pair, an empty pair, you can say, of electrons, or an empty pair meaning it'll have a place where a pair of electrons can come in and bond. And a Lewis base, well, here it says Lewis acids have to have an empty valence orbital. So here it is. Lewis bases, on the other hand, are defined as electron pair donors. So this substance having an electron pair can donate. Now this is kind of backwards from the original definition. Recall the original definition says an acid donates a proton. Here an acid accepts an electron. But it's actually the same thing, because you're looking at it from really two different directions. And here it says that anything that could be a Bronson-Lowry base is a Lewis base, because Lewis bases donate electron pairs, and the Arrhenius bases accept hydrogen ions. Well, hydrogen ions come in because you have this lone pair of electrons available. That's why it accepts this lone pair of electrons. So from the standard definition, the hydrogen is accepted by a base. From this definition, the electron pair teams up, you can say, with the hydrogen. So think of it this way. And here it says Lewis bases can interact with other things than just protons, and that's the power of the this category of acids and bases. So think about it a little bit. In fact, here what you have is you have a combination of two substances that don't really involve a hydrogen, and we can still think of this as a sort of acid-base type reaction. So we'll finish up with this example, and the example asks us to identify the Lewis acid and Lewis base among the reactants in each of the following reactions. So this is a standard acid-base reaction. Notice we kind of see a Cn- gaining a proton from water, and anytime you accept a proton, you're called a base. But from the standpoint of a Lewis base donates a pair of electrons. So if you take a look, Cn actually has a pair of electrons to donate, and that's really how it acquires, you can say, the H+. So Cn is the Lewis base, and then water then is the Lewis acid. Because the Lewis acid, you could say, accepts that pair of electrons. So from the standard definition, this is the same as we've always seen, both now from the Lewis base and from the Arrhenius, the original definition. In the second example, this is where it helps to define these as Lewis acids and bases, because here there is no hydrogen being given off or accepted. But this substance here, and it's kind of a strange substance, you've got nitrogen with 3 CH3 groups. And this nitrogen has a pair of electrons. So because this nitrogen has a pair of electrons, it can accept into here some other substance. But these are now called bases, Lewis bases. Lewis bases will donate an electron pair. So if you see that you have an open electron pair, this can be called a Lewis base. Again, this is going to be Lewis bases. And if one's a Lewis base, the other one must be a Lewis acid. And this Lewis acid, again, will be then accepting this pair of electrons. So hopefully this idea has added to your challenge or added to your richness of your understanding of acids and bases. And this concludes for us Lesson 5 of Chapter 16.